Welcome to SOS Shorts, where we show you the lab, the job site, and the shop floor of today's Canadian industry. I am Martha Breithaupt, your host of SOS Shorts, and today we are at e-Zinc, a purpose-driven energy company dedicated to building a future with affordable, clean, and reliable energy for all. e-Zinc's unique zinc-based long-duration energy storage technology is designed to enable a safe and cost-effective transition away from fossil fuel-powered energy sources to renewable ones. We explore their technology and their new experimental development facility to understand their state of science.
So Dr. Gregory Zong started in a 10-foot by 10-foot lab at Broy Engineering, and working just by himself on the very first prototypes of this technology. And he did that for several years, and then he won some grant funding and moved into his first major space, which was about 2,500 square feet from about 2015 through 2018. And that's when I joined. And then after we raised our first capital in 2020, we expanded into a second facility that was about 13,000 square feet. And then grew from there and got another facility that was about 8,000 square feet. And then a third facility that we sublet with another few thousand square feet. But we knew that we needed to bring this all together because we were starting to get fragmented across multiple facilities. So we actually just moved into this new facility this summer. So this is a 42,000 square foot facility, and we managed to collapse all of the other leases and move everyone here under one roof. So it's very exciting because we haven't been together in one location for several years now. So.
Excellent. And so tell us a little bit about the technology used here at e-Zinc.
Yeah, so the technology is a proprietary zinc-based electrochemistry. And we have a cell, but it's not a cell like traditional battery cells. It looks like a small fish tank, like about a foot wide, foot tall by 3 feet deep. The whole thing is submerged in a bath of electrolyte, so potassium hydroxide, with dissolved zinc in it. And when we inject energy into the system, the zinc precipitates out as physical zinc metal on the electrodes at the top. We have a physical wiping mechanism that wipes the zinc off, and it falls via gravity like snow and settles in the bottom of the cell. And that physical zinc metal is the stored energy. So we call it metallizing energy. We've literally turned energy into a physical substance. Then when we need the energy, we inject air into the system, and the oxygen dissolves the zinc back into the electrolyte, and the dissolution of the zinc is what frees the electrons, allowing us to discharge the energy. So now that the zinc is redissolved back into the electrolyte, the whole process can be repeated. So it's fully rechargeable, and it's the state change of zinc between solid and dissolved state. So the analogy I like using is like sugar dissolving in water. If you could take energy to recrystallize that sugar, and the dissolution of that sugar into water was what created energy, that's what we're doing. We're just using zinc.
Tyler shows us the R&D lab where accelerated life testing, failure, and performance testing occur.
So this is really where we do all of our durability testing. We set up things and we run them until failure. We have this fridge right behind you that acts as our makeshift environmental chamber. Just studying the low temperature effects, simulating what they may encounter in the environment when the product's running is really important. And we found a really cost-effective way to do that with just a simple fridge. That's easy to do because our battery is a water-based system. With something like the lithium-ion battery, it's more organic, it's flammable. This wouldn't be well suited, but since there's no explosion hazards with our materials, we can just use something simple like that. We're testing different electrodes. Essentially, we set up shells of these different replicates. We want to get statistical data on all the experiments that we're doing. We run them at different operating conditions, and just to understand what that response is. So here we're testing different variations of electrodes, different operating parameters, different airflow rates even is possible with this setup. This is a really, I would say, good design of test fixtures, so we can then scale up to thousands eventually. So within the R&D lab, one of the things that we want to do is break down component performance to isolate any effects that the system may have on it. So when we look at the full cell, they're very complex. There's a lot of things going on, and it's really hard to understand what changes may be happening or how something may be performing on its own. So what we do here is we design different test fixtures to study what those component performances and what effects may have in isolation of the system, so we can build up a holistic model of what the performance of the system may be. More of a bottoms-up approach. Also, it helps root cause any troubles that we may have in the cell, especially as we look to advance different components and innovations forward. I'm showing 3 test fixtures here that study different things. Here we use just a simple electrochemical cell that has an output that we can then hook up to any sensors. This is a little bit bigger. We can study larger electrodes, but we have a place for sensors here. This we can actually study how different water pressure effects have on electrodes that sit at the bottom of our cell. So as we increase the height of the cell, there's going to be more pressure acting upon the bottom of it. And so we can study how that affects degradation and performance as well. In this fixture, we can study both our charging and discharging system because it has 2 sections. So we can scale up the electrode studied here and also add in a little bit more complexity that would represent our full cell by adding a discharge section in the bottom where we're studying different air cathodes, for example, different formulations of that electrode. Within all of these, we can also study different electrolytes, different concentrations, different additives. Those all have a pretty large effect on the performance and functionality of the cell. What we have here is some equipment that's hooked up to an environmental chamber. What this does is it studies the effect of temperature and different humidity on our component performance, really to understand how things may perform or degrade within the field. We have a number of different electrochemical instruments feeding into this, a data acquisition system that's measuring the data output from the fixture, as well as various sensors that capture all the information that we need to do in order to understand the system.
David, the senior machinist at e-Zinc, brings ideas and innovations to physical reality by using CNC machines, programming, and other tools to build prototype parts and test fixtures.
Yeah, sometimes it's a full design. Sometimes it's just like a sketch or an idea, or it might be a part, and they'll say like, "Hey, David, I have this, but can you make it like sort of this different way?" And I'll sort of figure out a bunch of different ways to do things, and there's always like a million ways to do everything. But then we settle on something, and then we make it, and making it is really like part of the fun. So yeah. So some of the design considerations are the chemicals that we'll be working with. So compatibility is a big issue. So for instance, some of the chemicals react strongly with aluminum, so we can't use aluminum for a design, so we'll just use a different material. So chemical compatibility is one. Also, strength is another one. So we'll have different things that need like different levels of strength. So that's something we think about as well. Conductivity is a big one. So copper is very conductive, so it's very good for transmitting electricity. Heat is also a big issue. So certain metals have different characteristics with heat. So steel has very high localized heat, whereas something like aluminum will heat up. If you heat one spot of it up, the whole thing will heat up. So it's very important to think about all of these different characteristics. And it's really fun working with different materials. So this is a CNC router. It's computer controlled, so I have it controlled with my computer right here, and it takes really simple directions. So it's like turn the spindle on, so this end mill here will start spinning, and that's like what cuts into the part and makes what we're trying to make. But it takes really simple instructions called G-code, and there are things like coordinates. So it's like so you have like the x-axis here and the y-axis there, and then this is the z-axis. You basically program this in a way where you're going to different coordinates. So if you're into algebra, like this is the machine for you. So this shows you what the tool path is going to be like before we actually do it, and we can actually simulate it as well. So I'll just do a little simulation, and we can kind of see what will happen before it happens. Once we're like happy with how the program is, then we can send it over to the router itself, and then yeah, we can start the jobs.
The test batteries move from the machining area and R&D lab to the prototype assembly area, where Natalie wires and configures a new battery setup for testing.
And yeah, I'm at e-Zinc. I work as a mechatronics engineering specialist. So I graduated from U of T in mechanical engineering. I specialized in mechatronics. So that's kind of a mix of mechanical and electrical engineering. So I do a little bit of both here. So that's like, I touched a lot on programming things in Python and C. I do a lot of SolidWorks design, CAD design, things like that. And I also make a lot of like hands-on products that we use in-house right now. I've been working on wiring this up. So this is used in our PCS system. So this system kind of controls our charging and our discharging of the batteries. So this is particularly the charge side of the battery. A lot of it just is going to connect to the battery itself and just all of our controls, so we can tell it, okay, here's how much current we want to send to the batteries. So just general wiring. I make the cabling for this. We have like these wiring diagrams that I'm following right now, and I just connect all of this stuff inside. So it's just a lot of like cutting, stripping, nice clean routing of wires that I'm doing here. This is kind of what we talk to control all the systems inside of this. So that's the red board you see here. These are two fans. This is wired to the EPS, just cools things down, which is also what these big silver things are for. These are just heat sinks. So they help cool down these big boards, which take in the charge from the batteries and everything. Then this little board up here, this controls a lot of thermistors. So thermistors are things that kind of measure the temperature of different components that they're connected to right now using just resistive values. And yeah, so everything's just mainly connected to this board. That's our main controller.
Excellent.
So next, I'm going to be slotting it in over here. We just do like a test sequence. So we're going to power it on. This is just a panel to power everything on together and make sure it all works and integrates well. So we power this on. Right now it's not connected to anything, but if it was, this would send power to our EPS. And then we control that using just a laptop. We plug it in through we have just some cabling here that kind of goes to the laptop. And then we're just going to run the fans, make sure that we're getting data through CAN from our EPS and everything. And if it all works, then we can slot it into one of our final racks, and then we can use it to help discharge and charge our batteries. Our work also includes integrating it with the battery test team in the container. So right now we're working on this big container. It's called our CEC project. And we're going to be putting all this stuff in big racks in this container, making sure it all works together as one system. So that's kind of what our team specializes in. We don't touch too much on the batteries, but yeah, kind of everything behind the batteries, all the electronics, everything, make sure it all smoothly comes together into one final product.
Excellent. That's wonderful. Thank you for sharing that with us.
Of course.
Once a prototype has been designed, fabricated, and configured, the battery units are moved to the test lab, where Stephen, a master's in chemical engineering from the University of Waterloo, shows us how the e-Zinc battery system has the ability to scale energy capacity independently from power, enabling various market applications.
Yeah, so this is the cell test lab. The main thing that we do in here is we test our prototype cells, which are in those test bays over there. We also store various chemicals, and we do sort of more benchtop experiments like you can kind of see over here. We've got support systems like the air system that's over there, and various computer systems to monitor everything. Lots of storage over there. So this is, in many ways, the heart of the facility. We do all our design work, we do all our calculations to see if what we want the prototypes to do should work, and then here's where the rubber meets the road. We do sort of standardized testing to make sure it's meeting the performance specifications that it needs to, and then we also do sort of special tests to test like specific problems that could happen in the field, like it could be high temperature testing or a specific operating condition, something like that. Yeah, so over here are some of the cells. These are older models. There's a new one that's going to be coming out early next year. And yeah, they're manufactured in-house by our manufacturing team. And these ones are shorter duration. They do about 10 hours of discharge. But it's very easy to just make them taller, and they can do 24 hours of discharge or 48 hours of discharge, whatever the market demands. It's one of the big advantages of our technology. These cells are rated for about 100 watts of power discharge each, so you get 10 to get a kilowatt, roughly. And in the mixing room over there, we have a 180-liter reactor where we mix the liquid that goes into the cells, and it sort of is the glue that holds the cell together. It makes sure that all the electrodes are connected electrically, basically, so that the reaction can actually happen. And so the procedure that we have is very involved. We're working on simplifying it and finding easier ways of making it. But for now, what we have in there makes what we need, and to the specifications that we need to. In fact, we finished a batch yesterday. Today we're going to do all the quality control checks on that batch. So here's our setup. This is the batch we just finished. We've left it there overnight, and now that it's morning, we'll do the quality control batches. That's the actual pilot scale mixer. We've affectionately named it Frodo. This is where all the magic happens. It's got a heater. You can see it's got the impeller. That's the green thing that's sticking in. And then this is support systems for this. Over here is our smaller, more advanced reactor. So this is for making lab scale batches for testing out different recipes, right? So if you want to make something that's higher energy density or has this particular additive, or if you even just want to figure out an easier way to make the electrolyte, we would do it here, so we don't have to be doing it 180 liters at a time. This one's Samwise. And it's pure Teflon. It's got very tight control, more so than this one. This is more advanced. So we're testing all different conditions to see what's the best combination. And then once we get the results from that, we'll pick 2 or 3 of those combinations. We'll do more in-depth testing on that, still on the bench, to see like, can it survive high temperatures? Can it survive, like if you get some CO2 in it, is that a problem? Or other like specific conditions like that. And then once that passes that, then we would make a large amount and test in the full cell.
Using engineering, math, chemistry, and machining, the e-Zinc team is developing a low-cost, scalable solution for our ever-expanding energy consumption needs.
I think I didn't really even understand how complex this business was when I got involved. It involves electrochemistry, mechanical engineering, electrical engineering, software and controls. It's the confluence of all of those things, right? So, I mean, fundamentally, it's an electrochemical system. So you have a whole bunch of complex reactions happening inside the technology. You have electrolysis, you have the formation of zinc, you have oxygen reduction reactions in the discharge. So there's a lot of complexity in the electrochemistry. Then you also have the mechanical engineering, because it's a physical cell and it has mechanical components. It has a pump that recirculates the electrolyte. It has a motor that powers the wiping mechanism that shears the zinc off of the electrodes. Plus, it's a physical cell that you have to construct and manufacture. Then you have the electrical engineering, because those cells are only usable if they have all of the power electronics. So equipment that converts the DC power to AC power, so direct current to alternating current, or the circuitry that isolates cells or switches cells between charge and discharge. And then you have the software and controls as a layer sitting on top of all of that architecture to control it.
e-Zinc's long-duration energy storage technology is a paradigm shift in energy storage to enable a zero-carbon energy future, which is reliable, safe, long-duration, recyclable, and reusable. Thank you, James, Tyler, David, Natalie, Stephen, and the entire team at e-Zinc for sharing your state of science.